hear me better because you see we have some pumps working and a bit of noise. So we are now at powder diffraction beamline. So this beamline was created having in mind all the possible diffraction experiments that can come from Spanish community. So it's very versatile. It can work in different configurations depending on the task. To do this, we have two experimental stations here. One, which we see here on the right from you. This is the station for high pressure and micro diffraction experiment. Here we focus the beam down to 15 to 20 micrometers in size. We have focusing mirror here inside this box. And so we put the sample here and measure it, collect the data using the two-dimensional detector. So as you saw this afternoon, so we measure the whole ring and then integrate around the ring. So because of very small beam size, we can essentially scan the object and analyze the structure in different parts, which is very widely used, for example, by historical archaeological community to analyze the cultural heritage objects. And also we can put the material inside so-called diamond anvil cell, the device that is used to create high pressure, where also the material is fixed between two diamonds, and the diameter of the diamonds is order of 100 microns. So again, we need very small beam to do this. Another station over there in the back, it is designed for more classical experiments, something that looks quite similar to what you might see with your laboratory diffractometer. So we have goniometer, we can scan the angles with the detector, and we have essentially two detectors here. The one on top is a high resolution point detector. So here we really have to scan it across the angles to collect good data, but the positive thing is that the angular resolution is extremely high. We can separate very close peaks. The one at the bottom is a linear detector. Here we have a bit lower angular resolution, still much better that you might obtain with your laboratory diffractometer, but a bit less than here. Good thing is that experiment with this one is much faster. Normally we can follow the transformations inside the material in real time. So typical measurement time with this one is approximately 1 hour, maybe 40 minutes. And with this one, we can collect the pattern good enough for it with refinement already in 1 minute, normally. So, or even faster. It depends on the quality of the material itself. So the sample itself here looks like this. So we put the powder inside the capillary. The diameter of capillary can be different, again, depending on the sample. We normally measure in the range of from 0.3 millimeter to 1.5 millimeter. So, and then the capillary is mounted here and put under the beam. So the beam size here is 3 millimeters horizontally, and depending on the experiment, from 0.7 to 1.5 millimeters vertically. Also, we can put various sample environments in this station. Now, what you see here, it's one of the most complex. It is liquid helium cryostat. So this week, starting from tomorrow, we will have experiments at liquid helium temperatures. So here we have the liquid helium DR. There will be transfer lights sending helium from here to here, and the sample will go inside. For experiments at a bit higher temperatures, we have the cryostat that works with liquid nitrogen, so we can go down to, let's say, 90K. We can also go higher with temperature up to 1,000 degrees centigrade with hot air blower. And we can put here the gas cell to work under some atmosphere, non-ambient atmosphere. Or we can put here the holder for electrochemical cell and investigate electrochemical reactions. So this is is what we have from a technical point of view. Now we can go to control hatch, and I will show you how it works. So please take your seats. And here, so I will show you some stuff on this screen. What we do, how we do, depending on time, maybe a bit more, a bit less. With first group, we managed to see lots of things. With second group, we had more questions, so we didn't see everything that I could show. So it depends. So the basic sequence of analysis of the diffraction data, it is what you have here. You start, in fact, not with analysis, but with preparation of the data, because the detector gives you some raw data file that cannot be directly used by an external user. It does not fit to any reasonable program approach. So we have to prepare it. If it's two-dimensional data, we have to integrate it across the ring. If it is the data, for example, from mud detector, which in fact contains 13 channels, we need to merge the data from all the channels into one. So in reality, the user gets already the data ready for analysis in standard XY format, and something that can be used. If somebody does not like it, it can be transformed by, for example, PowerDLL program to any other formats that you like XDML, like Jesus format, and so on. But from this point already starts the responsibility of the user, unless, for example, some industrial users wants to pay us for analysis. Sometimes it happens, but not very often. So the analysis of the data can be done according to one of three paths, again, depending on the sample, depending on the task, and depending on the material that you want to analyze. So first sequence is phase analysis, so just comparison of your diffraction data with some database using different kinds of search match software, and just trying to find which phases you have and more or less estimate how much of each phase you have. The most, probably, I would say the most important thing is retrieval refinement, and today it's the default technique to analyze the powder diffraction data. So, in fact, I put this line, so because normally every time you will finish with this. If you have phase analysis, at the end you will do retrieval refinement. You have structure solution, you will do retrieval refinement in the end, anyway. So, and the third part, what I already mentioned, structure solution. This is the most complex task for powder diffraction technique, because compared to single crystal diffraction, we lose part of the data, and so it's not very easy to recover it. But it is possible in many, well, in some, at least in some cases. So depending on the, usually if it's possible, it is already done. But yeah, we have cases when we really did full structure solution from the powder data. So this exists. Okay, so this is more or less how it looks. Just a quick list of the programs that can be used. So we have integration programs for integration of two-dimensional data, like Fit2D or D2D plot. This one is developed here at Alma. We have the programs to create nice plots of many diffraction patterns, like 3D plots and everything. Of course, there are databases. Some of them are commercial, like PDF or ICSD. Some of them are free, like Mineralogy database or Crystallography Open database. And of course, there is phase analysis software that many people already have coming with their laboratory diffractometer, and you can import the data from synchrotron. And for solution and refinement, there is huge amount of programs. Depending on what you like, with which one you have experience, you can use any of them. Again, some of them are free, some of them are commercial. So this is how it works. Now I will quickly show you what we normally do with one, well, kind of basic example, not very sophisticated, something that we can do in the time that we have. So, what happened? The idea was to synthesize this copper iron oxide. And the question was very simple. Was the synthesis fine or not? Or were there some impurities? So this is the data file that we have. We have some header lines that we will now ignore, because otherwise the program will not understand what's going on. And we have the data: angle, intensity, and standard deviation. So this is the diffraction pattern. We can cut the low angle part because it contains some not very good data. And we can search for the peaks. Of course, the default peak search is never good, so we have to help the program to put some peaks manually. You see, we have lots of very small peaks. If you would measure the same sample with laboratory diffractometers, probably you would never see these peaks, for example. So let's this. I will just put more peaks to be sure that we really find everything that we can find from this pattern. Probably already default would be almost enough, but I want to be sure that we do not have to repeat everything from the beginning. You see, the peaks are really good even if we have this huge magnification. This is why you might need to go to Synchro to find all these. Okay, hope this will be enough. And okay, let me just quickly make. So here we have the search filter. The idea is that we do not want to scan through the whole database because it will find some completely unrealistic solution. So we can just use some subset, for example, battery material, cement material, explosives, or whatever, if we know that it is like this. We can limit with quality, with environment like temperature, pressure. In this case, I will not do this, but what I will do, I will make a chemical limitation. I will tell it that it should be oxide. It can be iron, copper, or both. Let's have a look what happens with this filter. So it tries to search. It gives us a list of the possible phases, and for each phases, it gives the figure of merit that tells us how good it corresponds to the experimental data. So, and we go from top to bottom, so we start with the first one, which is really the phase that we wanted to get, the copper iron oxide. So we accept this phase, but we immediately see that not all of the peaks were described. Like this was not described, this one was not described, this one was not described, so we have some impurities. The first impurity that we have is also mixed copper iron oxide, but with different element ratio. Instead of 1,1, it is 1,2. So we accept this. It corresponds, in fact, to this peak, and okay, many others, but this is easier to see. We still did not describe this one, and this one corresponds to iron oxide, iron plus 3. So, and if we accept iron oxide, the program tells that it cannot find anything more. And we have to stop here. And if we look at the table, we have more or less 79% by mass of the desired phase, but we have 10% of this impurity and 10% of this impurity. So if, for example, the only task would be to check if the phase is pure or not, you would have stopped here. But now, because we want to be able to do more, we now will try to refine the same diffraction pattern and try to find more information about this sample. So I will now go to Jesus2 program. It will take some time to start. Normally it happens faster. I don't know why now it does not want. I have. Is it? Okay. Yeah. Now it goes. Okay. So we have the program that essentially shows us two windows, one window for parameters of refinement and one window for plots. We import the same diffraction pattern here. Okay. So I will take the same one. And okay, we have the pattern. Also, I will cut the low angle part to make the things easier. And I will have to modify the wavelength because the default one is not completely correct. And of course, because it is refinement, so it means that we try to adjust the model, we have to import the starting model, which will be essentially the C file that I downloaded from the crystal structure database. So we will start with just one, see how it works with on the copper iron oxide. So you see, we can, in fact, refine many parameters. We can, of course, refine the lattice parameters here. We can refine the phase fraction. We can refine size. We can refine strain. And we can refine all the atomic parameters like coordinates, occupancy, or thermal oscillation parameters. Everything is here. So we will start with something very simple, because refinement is a non-linear task. It means that it easily diverges if you start with too many parameters. So we will go step by step. We'll start with refining the background and and the scale. So just the intensity. And okay, I will immediately put it here. And okay, let's try to see what happens if I refine only these two. I have to save it. So it does the refinement, and we can look here. Of course, at the beginning we see that it is not really good. So if we magnify this range, for example, we'll see, well, the peak is quite nice, but okay, we have all these impurity peaks, but maybe also the shape of the peaks is not very nice. Maybe it will be visible here. You see, it's quite narrow here, more broad here. It means that we have some not very good size. So we can try to improve it. First of all, of course, we will need to refine the lattice parameters because they might be different from default ones, and we will try to refine the size. Let's have a look what happens here. So it moves, you see the shape changes. Somehow it a little bit improved, but still not good because we have some discrepancy in intensity. It means that we also have to refine the atomic parameters. So what I will do, I will refine the thermal parameters for all three and position only for oxygen, because for these two it is fixed by symmetry of the unit cell. Let's try to do this. It improves a little bit more, but still not good. Here we start being affected by all these impurities that we did not include. So we import the impurity phases. So copper iron oxide, and we import the iron 203. Okay. So just to make things a bit easier to the program, I will put the better starting values just to make the refinement a bit faster, so that we do not spend too much time here. Okay, so I will refine the phase fraction and the lattice parameters for both of the phases. It's a bit, in fact, it's a bit risky approach, but I hope it will work. Let's try. Okay, yes, so iron oxide work, it was fine. Yeah, we have both of them. Okay. We have both phases. Again, probably they have some problems with size. We can try to refine the size to have better peak shape. It improves. Okay, you see the difference curves becomes better and better with each cycle, but still not perfect. Okay, then we can continue with all this until we have the data that looks good for us, because sometimes we just have to stop. We cannot find the parameter that would improve the data even more. But okay, I will let it to do one more cycle of refinement here. Maybe it will not change much. But you see now immediately that, in fact, we have more impurity peaks that we did not find with database search. Just because I know what it is, I will add. It is also iron oxide, but it is iron plus 2. I will take it from here. This one. Just because the database one, it required a bit more of refinement. I don't want to spend much time on this. So let's start with. Okay, and also it did not refine it very well, so I will not do real refinement of this one. Let's just look. So we have the peak here. Again, we immediately see that we might need to change the size or strength and everything, but we will not spend much time. So this is some more or less refined diffraction pattern, not perfect, but for our today's purpose, it's good enough. We can say that in our material, in reality, we had 75% of 1-1 phase. It is a bit different compared to what we had here, right? We had 79, so we have more precise result. 13% of this, almost 11% of this, and we have 0.9% of iron oxide, but we still see quite good peaks of this phase. So this is why you need synchrotron, because of course with laboratory diffractometer you would never see this phase. But here it is immediately visible that it exists. Okay, so here we can stop with this one. I don't know, Marta, we have lots of time, I guess.
You have more things.
Yeah, I have more things. I just want to be sure that I do not spend too much time. Okay. Okay, so we can. So maybe just if you have questions for this part, you can ask now, or if not, we will go to the next. Because with one group we managed, with one group I had lots of questions. I could not go to the next part. So, do you want to ask me now something about this? No. Yeah.
For the refinement process, for all the steps that you did, do you have a path to follow, or you are just changing things randomly?
No, it's not.
Experience.
Yeah, it's a bit of experience, or it's a bit of knowledge. So there is a logical sequence. So you start with parameters that affect the pattern a lot, and that are more stable, and then you go to more tiny details. So what normally happens, you start with background and overall intensity. Then you add the lattice parameters and maybe the phase fractions, and then you go to atomic parameters and the peak shapes. Usually it's more or less like this, and then it depends. So sometimes you have to also for atoms, you also have to go step by step, start from heavy atoms that affect more, and then go to lighter atoms that affect less. And then you might need to add more parameters, like, for example, preferred orientation. If your material is very anisotropic, it might not be really randomly oriented, and you might need to put these parameters also into consideration. So then it depends. You go more and more. Okay, so this is it. And now what the third thing that I showed you in the first slide, yes, we have three techniques that we need: phase search, relative refinement, and structure solution. So now we will try to do structure solution with the same phase, which is very simple and it should work. Of course, not with the real case, which is normally very time consuming. Okay, so let me start. We'll use another program, which is called Fox. Okay, so again, now I will skip many steps because the structure solution is the most complex task. It's not always working as it should, so I will have the program a lot. It will not be like we normally do this when we don't know anything about the structure. So we tell the program that we will have a crystal, we will have a diffraction pattern. So we import our diffraction pattern. I will take another one which was a bit better. It contained less impurities, but still it contains some of them. Of course, I have to tell it that we have some correct wavelength. We can have a look here. I will put it to the screen. As usual, we start with the background. So I tell the program that we will have the background over here. It will try to, maybe I will, okay. And I will try to redo it like this. So in fact, with this value, I just select the range that will be used for structure solution. And now, again, we do the same. We do the peak search. I will not change anything. I will not add extra peak. I will not remove the peaks that are wrong. I will just modify it later. So, and then we try to do the indexing. The indexing is essentially search for the unit cell that corresponds to the peak positions without taking into account the intensities of the peaks. So we'll do this, and in fact, if I do it like this, most likely I will get wrong result. Let's try. Yeah, this is not correct. I guess it is some subcell or some lower symmetry because it takes into account the peaks of impurities. I will help it a little bit. I will tell it that we have impurities. I will tell it that we should have a hexagonal cell. Do one more search. Now it is already better, but we have supercell. We put more along A and B axis. So I will now quickly accept this one. I will put correct parameters so that we can proceed to what we really need. So I say that we accept this one for our phase. I will go back to the crystal. I'll tell it that it's hexagonal, and I will just put the correct lattice parameter. That should be this one divided by square root of 3 multiplied by something. It should be 3 point whatever we had here. I will just take this one because we know that this one is correct. 3.03, okay? 3.03 as a starting point. I will tell it that we use this crystalline phase, and now we will do so-called Libel refinement. Again, this is refinement of intensities without taking into account the structure, just mathematical refinement. So we do it like this. First, we put zero shift background again in unit cell, the same as what we asked about the refinement. So we start with the most important ones and then go step by step. Now I add the width of the peaks. Then I add more details about the peak shape. Okay, now it should be enough. And the next step of structure solution is search for the real symmetry of our structure. So normally it is done using so-called systematic absences. So the positions of the peaks where the peak should exist there, but the intensity is 0 because of the symmetry of the crystal. So again, the program can do it for us, but otherwise you would have to go to so-called international tables for crystallography and do manual search. I hope you will not do this. Okay, so this is done, and in fact we have 5 options, the best ones in terms of goodness of fit. And well, I know that we should use this one. Otherwise, if I would not know, I would have to check all of them. So I go here, I put the correct symmetry here. Okay, this we can close. And now we will try to put the atoms inside the structure. So we will have here copper, we will have iron. In fact, from X-ray diffraction point of view, copper and iron are not very different, but it will not affect too much our calculation right now. And okay, I will add 1 copper atom, I will add 1 iron atom, I will add 1 oxygen atom. So in fact, in this structure, copper and iron are interchangeable. If we just change the origin, we will move between copper in 0, 0, 0 and iron in 0, 0, 0 position. So it's not a problem for us for now. So this is it, and I will put just some very random starting configuration. So if we plot this configuration here, of course it is something completely wrong, basically because if the atom is in general position by the symmetry elements, it creates many equivalents, much more than really should be here. So we know that it should go to special position, but let's see how it happens. So we create this optimization procedure. I tell it that I want to refine this crystal with respect to this diffraction pattern. And well, this is just Monte Carlo simulation. It will try to move the atoms around until it gets good fit. Okay, let me just try to put it like this so that we see everything at the same time. Okay, and I start the procedure. I will do single run, it should work. So you see, almost immediately it moved the atoms to much more realistic positions. And essentially it already stopped because the structure is very simple. For the complex structure, it would take much more time, much more refinement cycles. So normally it might take days until you reach the really good models. In our case, it's simple and we are already there. So this is it, and if we compare this with what we had here, essentially it's the same. Maybe it's... I will just plot the model that I put into our refinement. It was this one. So you see it's the same. Oops. The one that we got from the database and the one that we calculated right now, we have the same structure. Now again, so what would happen next if it would be a really new compound? I would take this model and then insert it into refinement program and optimize it until I have really good correlation between experimental and theoretical data. But from here, I have the starting model to do this. This happens if I do not have any database entry. Okay, so I guess that's all that I could show you about how it works, the main procedures that we do here. So we can stop here. I guess this is already this is already finished. So if you have any questions, any doubts, this time we have lots of time for your question.
Yeah, if you have questions or
yes.
you want to ask him.
Yeah, or not necessarily relating to what I showed you right now. Anything about powder diffraction, we have time to ask.
I have one, but I don't know if we have a semi-crystalline material And is there some software for doing the combination between the amorphous and the crystalline peaks that more or less works, or?
Okay, so there are different approaches. It might be that it is semi-crystalline in terms of some kind of disorder on top of your average structure, like turbostratic disorder or stacking fault disorder. This is one thing. Here you do, again, refinement, but with a bit more complex software like defects, like faults. So this can be done. Another thing, if you have some really amorphous component. In this case, standard powder diffraction does not give you information about amorphous material. You just have very broad peak. But there is another technique which is experimentally very similar, and it is done also here. It is powder pre-distribution function analysis. So what you really do is you can also collect diffraction data, but at much wider angular range and high energy to go really very fine, what is called inverse space. And then you do Fourier transformation, and what you get in this case is the pair distribution function, which shows you the distances between atoms. This is something similar to what you already saw at X-ray absorption beamline. The difference is that in their case, they are element sensitive, so they only create the bonds with respect to some certain elements. In pair distribution function analysis, you have all the interatomic distances inside the crystal. And then you can try to analyze it. People really do it. It's possible to model it, including the amorphous material. I don't know if I have it here. So I know that I have the program here, but I don't know if I have something to show you right now how it works. Yeah, maybe it's not so easy right now to find, because I did not prepare for this. It's separate task. But yes, it can be done.
Okay.
Again, there will be several levels of analysis, starting from very qualitative analysis, just to say, here we have these interatomic distances. It changes somehow depending on the conditions. For example, it's very typical for cements. Normally they have lots of amorphous phase, and they just look. So if some peak moves, and they make some conclusions from this. Or you can really try to model your material, which is much more complex. But the software exists. It's not so easy to use, but it's possible.
It's polymers that have segregated lamellas and
For polymers, yeah. Yeah, again, so for polymers, some of the polymers, the structure is not, it is solved, and you can use as a starting model and just try to apply this